Hey there, everyone. Welcome to my analytics channel. My name is Ryan Schul. And today in the narrative, I want to talk about predicting employee attrition and try to design targeted retention actions to keep the best employees with the enterprise, right? Now, there's always going to be people coming and going, especially in larger organizations, and there's always going to be some amount of attrition. We can predict some of this. Some of this might blindside us. Maybe we can't predict some of these, but I think in many cases they are there and they are targetable and actionable too. Okay, so let's take a look at how we can try to cut down on employee turnover, which can be very costly to any kind of firm, any enterprise, any type of corporation, right? Basically, you have 100 people or 1,000 or maybe 100,000 people. You can have an X number of people, N number of people, whatever you want to call it. If these people are trained with your company and they acquire a lot of knowledge, and all of a sudden one day they decide to go out the door, that's a lot of information, a lot of knowledge just walking out the door and probably going to work for your competitor, right? You don't necessarily want that. So what can you do to prevent that, right? You want to recruit smartly, onboard intelligently and efficiently, and control losses in terms of employees attritioning and leaving and going somewhere else. Either, if somebody goes to retire and they're old and they're just ready to slow down the pace of their life, there's nothing you can really do about that. Maybe you can retain them and have the person, be available 1, 2, maybe 3 days a week and give them like an extra long weekend every single week. You don't want them to go work for your competitor. It's going to take all your knowledge and skills, and it's going to be a disaster, right? When a bunch of people go work for the competition, right? So we want to prevent that. We want to do smart workforce planning, forecast likely exits based on teams, skills, geographies, hiring pipelines, trainings, cohorts, what kind of people tend to affiliate with other types of people and their peers in a capacity to, generate a lot of income for you, or to, again, leave and go work for the competitor. And that is going to be a nightmare come true, right? So a lot of this depends on actions of the employees, slights, indications, maybe nonverbal cues, things like that. We're not really going to focus too much on that. That's hard to capture and hard to analyze, right? But we do have some very actionable, very clean, crisp data that we can analyze, and we're going to try to understand the effectiveness of different managers, what kind of output or outcome that has if a manager is compassionate and engaged in their employees' success. That is going to have a lot to do with the employees staying on and continuing to work for the enterprise that you own and operate, right? If they don't like the manager and they don't like the environment that they're in, then they're probably going to walk, right? So we can try to identify that and prevent that from happening. There's a few other things we'll look at in terms of diversity, inclusion, continuity, compliance, operational risk, avoiding knowledge loss, right? You don't want these people walking out the door. And some of this has to do just with culture and employee branding, right? Employer branding, and proactively addressing pain points to reduce regrettable losses, right? If you kind of squeeze out an employee because you're flexing or you're showing them that you're a powerful manager or something, and they don't like that, you can push them right out the door, and that's gone for good, right? That's never coming back. That happened to me a couple of times. I actually got pushed out. I was making a lot of money for a lot of people, and for whatever reason, they just said, "Listen, I'm strong. I'm going to flex my muscles." I didn't like it, and I left, and it worked to their detriment. So you have to be careful with these things, because it can come back and bite you. So let me show you the data set that we're working with. I found this on Kaggle. This is consisting of 24 columns, right? And we have things like employee ID, age, gender, years at the company, job role, work-life balance, job satisfaction, performance rating, number of promotions, overtime, distance from home, education level, marital status, number of dependents, job level, company size, company tenure, leadership opportunities, innovation opportunities, company reputation, employee recognition, and attrition. And eventually we're trying to predict this column. Column X, is it going to be attrition equals stayed with the company or attrition equals left? Okay, it's a binary outcome. It's either one or the other. It's not both, it's not neither, right? So let's take a look at this here. And by the way, you can find this data, you can download it right here. I put the link right here at the bottom of the Jupyter Notebook. So you'll have that when you download the code, you'll have the link right at the bottom here. This is the end of the teaching lesson. Okay, so you'll have that right there. So let's just jump right in. So I have the normal libraries I need to run the types of analytics I'm going to run here. We have two data sets. One is training, one is testing. In the data science and machine learning world, you always do the training and the testing. The training can be 70, 75%, maybe 80%. It's somewhat arbitrary. You decide what that's going to be. By default, I believe it's 70% if you don't define it. And the testing phase is almost like you are taking a test in middle school or high school or college or grad school or whatever the case is, right? So the training, go to class, go to the lecture, interact with the professor, learn, read, observe, take notes, do the homework, things like that, right? You read all the reading lessons. The testing is when you sit down at the test, regurgitate all the information, and based on the outcome of the test, how well did you perform? How well did you generally learn the knowledge and extrapolate that knowledge to solve a bunch of questions that you probably haven't seen before, but you've probably seen somewhat substantially similar questions, okay? So that's the training, that's the testing. I discuss it a lot in my data science machine learning YouTube channel here. You can see all that. I've got hundreds of videos that discuss how that works. So you can see the headers over here. This is the data frame we just looked at, right? And all these features are going to have some type of impact on the attrition. And I'll show you how this works in a minute. Just a quick overview. Does a person work a lot of overtime? Yes or no? If they work a lot of overtime, is the person likely to leave? There could be, and it probably is, a high correlation between not a lot of overtime and a person staying. Okay, you see two cases right there, right here. Stayed. In all these cases, it's true. So there's not a lot of overtime, and the person stayed. Overtime, yes, person stayed. Overtime, yes, person left. Overtime, yes, person stayed. Overtime, yes, person left. And overtime worked, yes, and the person stayed, right? So that's just one example. We're going to look at a bunch. Distance from home is a long commute. Maybe the person is not going to stay too long. Education level, marital status, number of dependents, company size. All of these are features that have some type of predictive influence on the target variable, which is whether or not the employee left the company or stayed with the company. So we loaded the data into the data frame and reviewed it. Let's go ahead and set up some basic analysis here. Right now, I want to identify and normalize the target column, which again is, did the employee stay or did they leave? It's a binary outcome, can't be both, and has to be one or the other. Okay, so we have the target column. This is stayed or left. We are going to set up a short UDF. This is a user-defined function. Left equals 1, resigned equals 1, quit equals 1, terminated equals 1, separated equals 1. So positive is attrition. Any of these is 1, right? So if any of these is true, and we know in this case, right, I'm setting this up to be kind of general, but we know attrition is either stayed or left. The attrition could be quit, could be terminated, could be separated, could be 1. If the person left, it's a 1, that's a positive. If the person did not leave, that's 0, that's not, that's, what's the word? That's not matching with left, so that's stayed, right? So the point is, it can be a few different terminology things that come up here: stay, stayed, active, employed, no, false. Did the person stay, they stayed, or they left? Okay, so hopefully it's pretty obvious. So let's move down here, and we're gonna create some training labels, right? So this is basically a classification type of problem. Anything that's regression, that's time continuous, or numerical continuous, or some such thing like this. Control Enter to run. I just saw a mistake here. Is this target 1 train? Let me look into this for 1 second. Again, this is a classification type of problem. We're trying to determine the person stayed or left. Is a binary outcome. That's a classifier. If it's continuous, either time continuous or numerically continuous, or temperature throughout the day can be continuous, right? The temperature in the morning can be 60, can get up to 90 by the afternoon, go down to 60, and again in the afternoon. That's a regression problem. It's not a classification problem. You're not trying to predict, is it sunny? Is it overcast? Is it hazy? Is it cool and breezy? Those would be classifying outcomes, right? These are outcomes where we can define a specific result, right? If it's continuous, it could be any one of thousands of different outcomes, right? The time during the day can be seconds, it can be milliseconds, it can be a tiny fraction of a second. The temperature can be 59 degrees, 59.10, 59.11, 59.12, 59.13. It can be continuous throughout the day, right? So it's a regression problem. We are trying to solve for a classification problem. Okay, so continuing on, we have the user-defined function, define target, And we are looking again at different outcomes here. This is a binary outcome. The person stayed or they left, and left can be defined as left, resigned, terminated, separated, yes, left, right, or stayed. It can only be one or the other. Stayed could be active, employed, no, not left, or left, false. Okay, so these are the only outcomes. We have the Y train and Y test, and the X train and the X test. And again, the training is going to class, taking notes, doing the homework. The test is when you get into the test. You have a midterm and a final. Maybe you'll have 3 tests, whatever. You have to regurgitate that information and try to perform to the best of your capacity, right? So you can maybe get a 70, 80, 90, 100, make perfect score on the test. You've learned everything from the course and you have passed the test if you get 100, right? So the machine is basically doing the same thing. If it's getting 70, 80, 90, or 100, that's how well the machine is learning the material and making predictions into the future on unseen data that it has not been exposed to yet, right? So this is the ability of the machine to take information, generalize it to unseen data, and make sense of that unseen data. If it's seen it, it's literally just going to memorize what is already seen. That's why you have to change the pattern, the results, the questions that you propose to the computer to see how well it has actually learned or how well it has not learned, right? So that's the point of the training and testing. And we look at a couple cases over here. And we see here, so employee age, gender, years at company. This is what we saw over here before, right? And then the final prediction is the target variable is attrition, stayed or left. And we can see the target variable stayed or left here. That's what we get. So stayed 52%, left 47%. So this is important. So we know that the data set is basically balanced. And a lot of these classification types of data sets, you will see highly, highly, highly imbalanced data. So an example would be fraud data, right? If you see credit card transactions, most of the credit card transactions, probably 99%, more than 99%, will probably be legitimate credit card transactions, but some will be fraudulent credit card transactions, right? So how do you determine fraud from legit when 99% of the transactions are legitimate? The computer's going to learn most cases are going to be legit. When it sees a fraud case, it might make a mistake because only 1% or probably less than 1% of the time it's actually exposed to fraud. So it sees this so infrequently, it can't really learn what is fraud and what is not fraud. So the computer and people too, if they do this, tend to say everything is not fraud because it's mostly what they understand. But there are fraud cases from time to time, right? And you have to identify those and prevent those fraud transactions from clearing the credit card, right? You want to block it and stop it right there at the point of sale, right? At the cash register, or, if you're doing the some online transaction, that's the point of sale online. You want to prevent that. So those imbalanced data sets can be handled using SMOTE or a variety of other features where you oversample from the underrepresented class and undersample from the overrepresented class. In this case, we don't have to do any of that because the data set is pretty well balanced. It's almost 50-50. We see 52-47. That's good enough for me. I'm not going to mess around with this too much. It's pretty well balanced. So we can see the number of columns are numeric and categorical. A numeric column would be this, distance from home. That's a number, right? This is a categorical column. Categorical, this is a number. Categorical, this is a number. Company tenure, these are all categorical. So hopefully you get the idea here. These are categorical, all right? This is number, right? So anything that looks like a number is a number. If it's a category, it's a category. We have to convert categories into numbers. So we're going to do a one-hot encoding process. There's a few different ways to do this. I have an excellent video on my channel about one-hot encoding, label encoding, and what is it called? Categorical encoding. Those are the 3 types, right? One-hot encoding, categorical encoding, and geez, I just forgot. What was it? What was the third one? Categorical, one-hot encoding, and label encoding, right? So there's pros and cons of each one. You can go ahead and check out the video, and you'll see in which cases you should use which encoder, in which cases you should use others, right? The 3 main types, and depending on the scenario you're working with, you pick the best tool for the job. I always try to pick the best tool for the job. I tell everyone to do that. Sometimes people do it, sometimes they don't. So here we have the X training and X validation, Y training and Y validation. Remember, we split it, X and Y. X is the independent variable, Y is the dependent, and we have the training and the testing phases. So I'm not going to get into it too much, but that is basically how we set up the machine to do these learning exercises, okay? Okay, so there's training, there's the testing. We have X train, Y test, X train, Y train. We're going to fit that into a model called calibrated. This model comes from here. If I do Control F, you can see calibrated is the pipeline. We look at the um, pre right there, and the CLF is the classifier. This is a CV classifier, and we're using log regression. It sounds like a regressor, but it's actually a classifier. It I think it starts as a regression problem, but it quickly turns into a classification problem. I forgot why log regression is actually a classifier. Let me look this up. Why? Like it starts as regression and then converts into a classifier because it's core regression model that predicts probability of a class. Okay, so it's predicting the probability of a class, continuous variable 0 and 1, and a classifier comes from how this probability is used to make final classifications by applying the threshold, so it's just 0.5. So at the core, it's a regression model, it's a regression algorithm, but it predicts like a classifier, so it has a binary outcome, 0 or 1. Okay, so it's kind of what I thought. I kind of forgot some of the details in there. So yeah, so log regression is a classifier. We're going to go ahead and run this, look at some classification metrics. So you have things like accuracy, precision, recall, F1 score. So all of these metrics are looked at together comprehensively. Here's precision and recall, right? All of these are under the umbrella of a classifier, and we use this to try to accurately predict how well we can classify, to what degree of accuracy we can classify the outcome, right? So here we have AUC, this is the area under the curve. This is precision, average precision, area under the curve, and this is Brier, which is another type of statistical metric, which helps us determine how accurate this classifier is in making predictions into what the outcome is going to be. So 0.97 is almost 80%. It's about 80% accurate. That's pretty decent. We could mess around with the hyperparameters a little bit and get that a little bit tighter and get that boosted up to maybe 0.8 or 0.9, or just pick a different classifier. That's another path we can follow to try to get this number higher. Again, 0.8 is okay. It's acceptable in this scenario. I'm not trying to predict, I'm not trying to get the best possible accuracy or recall from this classifier. I have other videos on my YouTube channel that describe how to do that. That is not the goal here today, so I'm not going to spend a lot of time with that. 0.79 is bearable. That I can live with that. That is okay. Again, higher is better, but again, 0.79, it's okay. We can deal with it. So AUC, area under the curve, is good ranking. 80% of the time it's going to be accurate. 20% it's off. That's okay. We can live with it. In this case, we're not looking at accuracies of classifiers today. Those are videos for another day, right? So let me change the format of this just a bit. Given strong class imbalance, we don't have class imbalance, so this is not really an issue that we have to deal with. Again, if we did, we could use smoke or oversample from the underrepresented class and undersample from the overrepresented class. Okay, that's not an issue, so we're just going to move on. Let's look at sklearn metrics. We are going to look at some of these ROC scores, average precision, F1 score, precision, recall, right? Things like this. So let me go ahead and run this. Control Enter to run this. And we're going to get the outcome right here. UDIN and F1 is 0.39. Accuracy is 0.5. Again, a little bit on the low side. I would like to see these numbers a little bit higher. But for what we're trying to do today, I think this is okay. This is on a video about boosting the accuracy or the precision or recall F1 score of a classifier. Again, I have other videos on how to do that. We're just trying to pick a classifier, get it to run, and look at the outcome and interpret the outcome based on employee attrition. That's the goal today. So let's say on target here. So we have these accuracies over here. 0.75 accuracy, 0.71. Okay, it's okay. 0.7 and over is statistically significant, so I'll take it. This is pretty close if you average up or there. This is coming in a little bit under, but again, it's good enough for our purposes. Okay, so 0.7, basically 0.07 over right there. AOC 0.08, almost 0.8. I'm sorry, 0.8. So I think we are fine there. We can move on. We're just looking for the accuracy of the algorithm to make predictions into the future based on unseen data sets, right? This is abstract data that hasn't been exposed to yet, and it's trying to generalize on this unseen data and make predictions, and we're going to match the actual prediction with the original number that we derived from the data set. This is a holdout data set, right? This is the Y testing that we haven't exposed to the model yet. So it hasn't seen it. So it's making predictions. So we're going to match the prediction with the actual and see how close we're getting. That's how we're getting this 0.79, 0.78, 80% of the time it's correct. 20% of the time it's not correct. Okay, let's move on here. Score all rows and keep the score in a data frame. So again, we're looking at attrition probability. Sorry, I almost misspoke. Not quite. It's a mouthful, guys. It's a mouthful. And I'll admit I can't talk very clearly. I don't know why. I grew up in Connecticut. Spent my whole life in America. Some people talk elegant and crisp, clean, clear. I just can't do that. I don't know why. I just try to speak, and half the time it works, half the time it doesn't. Or maybe 0.79% of the time I can talk, and 0.78% of the time I can talk. The other time it's, I don't know, my brain is acting too fast and my tongue can't keep up. So attribution, sorry, I said that wrong again. Attrition probability. Attribution is we attribute some outcome to something. Attrition is when something is wearing out or leaving, right? So attrition, not attribution. I'm sorry, misspoke again. Attrition probability, right? So what is the probability of a person leaving this corporation and going somewhere else? Maybe exiting from the industry, maybe going to work in a completely different sector or different industry or something, right? Maybe that's the case. Maybe going to work for the competitor. That's the worst case scenario. Maybe retiring. Maybe just burn out. And they just need a year to do nothing, right? And just to not debrief, but just to debrief, digest. What's the term? Get all the stress out, de-stress or whatever, right? De-stress. Maybe they're just taking some time off. So this is where we are at this point in time, right? So we have the original data set. This is all the uppercase feature lists over here. These are the columns, uppercase letters. Remember, we got over to, where did we leave off? Let me go back just a couple of steps here. We got over to, where did we leave off? Right over here. Attrition, employee recognition, attrition. Okay, yeah, so we had the attrition, that's the target variable. And okay, so this was the original data frame, right? Company, reputation, employee recognition, and attrition. This is the person stayed or left, right? Let me look this up real quick. This is coming from over here, training. If we go back to the original data frame, just for me to get my bearings, that's what this is for. So we have employee recognition and attrition, right? So we go back over here. That's where we end up with, right? So company reputation, employee, what is it? Expand all these things over here. Let's make it a little bit easier to read. Okay. Company reputation and employee recognition and attrition, right? So this was the original data frame, company reputation, employee recognition, attrition. We just calculate attrition probability. So now this is the probability of the person to attrition from the company or leave the company, right? So anything that is a high risk, we have to identify this if we consider this employee to be valuable, and most should be valuable. Otherwise, if you're operating in the bottom 10% of the ranking of the overall quality of the employee, maybe you don't even want that person to stay around. Maybe they're dragging down the team or several teams, right? If the work is counterproductive or their person's combative or argumentative or something like that, maybe you want the person gone, right? So look at the attrition probability, and is this somebody that you want to keep? Probably 80 to 90% of the time you want to keep the person. Maybe 10% of the time it's just dead weight and you just want the person gone anyway. So if they fall into the bucket of most likely to attrition and the ranking of this person is the bottom 10%, probably just get rid of the person or just let them leave all on their own. If you fire the person, you're going to have to pay out unused not medical vacation, unused vacation days, maybe sick days, something like that, right? So it could be pretty costly if you just terminate the person. But if you know that they're seriously underperforming, bottom 10%, and this person is likely to attrition anyways, just let them, do themselves in, and they will just walk away all by themselves. So that is something that we have to be aware of. And then the risk bucket. Now we can assign these people into deciles of 10. So we started with around 60,000 records, right? So 60,000 people in this data set. We have 59598, almost 60,000. I'm going to say for all intents and purposes, this is 60,000 employees. We have deciles of 10. So 0 through 9, okay, we're assigning based on the, here's the risk bucket, based on the cut score, PD cut. You can look this up if you don't know what this is, PD cut or quartile. We can look at different groupings of PD cut. Let's see, Python. There's an excellent explanation of this, and it was right over here. I think this is the one, pandas PD cut. No, that's not what I was thinking. It was something else. They have a very nice overview, excellent explanation of how this works. I don't see it here. That's okay. You can look at any kind of documentation and get the general idea. PD cut is quantile-based discretization function where we break something into a certain number of bins or outcomes, right? In this case, it's going to be deciles. So it's going to be 10. We're going to go from 0 up to 9. So this is decile 2, 3, 3, 3, 8. And this is based on the attrition probability, right? So these three are pretty similar, 2, 6, 2, 9, 2, 9. So they all go into decile 3. See how the attrition probability is somewhat similar? This is going to decile 2 because the attrition probability is a little bit different. And this attrition probability is different, right? This is 0.63, 0.29, 0.29, 0.26. These are all threes. 0.20 goes into decile 2. 0.63 goes into decile 8, right? So we're taking the attrition probability and putting them into risk buckets. How risky is it for this person to leave from the perspective of the company, right? It's somebody that we want to keep on the payroll. We want to keep with the company, and it looks like they're probably going to leave. This is high attrition probability. We have to have a meeting with this person and make sure that they're appreciated. Maybe they need, financial support to take a course for some educational purpose. Maybe they need a slight boost in salary or like a one-time spot bonus. Hey, we appreciate what you do. We really want you to stick around for another couple of years. Please don't leave. So these are the opportunities to intervene here, look at what the potential for risk of attrition is, and quantify these based on the probability of attrition and put these into buckets. Then we can focus on certain buckets, right? Like if we want to keep the top 9 buckets, 0 through 8, right? And maybe 9, we'll let go with just saying, this is a hopeless cause. These people are lost. If you fall into decile 9, it's really bucket 10, 1 to 10, 0 to 9 is the same thing. Just let them go. If they fall in the other 9 buckets and we want to keep this person, we're going to have to bend over backwards and figure out what we have to do to cater to the needs of this person and keep them on the payroll, right? And so we're going to use a custom transformer here, looking for numerical features and categorical features. So I think I explained that before. Anything like this, number of dependents is numerical, that's numeric. These are all categorical. Anything that's not numeric is categorical. This is numeric, this is numeric. Monthly income, certainly numeric. These 3 over here are categorical, right? So you have to understand the numeric and categorical. If they're categorical, we have to create numeric representations of this using some type of one-hot encoding, label encoding, or categorical encoding. These are the 3 ways to convert a label or a non-numerical data point into a numerical data point, so we can feed it into the ML algorithm and have it make predictions into the future about the different outcomes here for these different individuals. So that's exactly what we're doing. Anything that's categorical, we are creating a number representation of that. We're feeding it into this model right here. XGB is extreme gradient booster, and XT is a transform for the X value. So this is X training, X value, okay? And we're looking at SHAP explainer. So SHAP is a way to break down the different categories of employees and look at, based on the feature of the employee, how much impact does that feature have on the target variable, and the outcome variable is the person likely to leave or not. So we are going to go ahead and create a SHAP outcome here. The output of this is job entry level, 0.50, variable status single. This is all coming from SHAP right over here. So SHAP values, you see right here, and SHAP values, if I do Control F, you can see it feeds down here. So everything flows. It flows from upper level down to a lower level. We are looking at the absolute value of the SHAP values, looking at the mean, and sorting all of these in descending order. So Job entry level, marital status, single or married, number of promotions, job level senior, distance from home, work-life balance. Remote work, no. Gender, female or male. Remote work, yes. Work-life balance is good. Gender is male, company reputation is good, number of dependents, and work-life balance, excellent. So all of these features are what we fed in from the original data set, right? You saw that in the CSV file. What has the most impact on a person leaving? The number one impact is this an entry-level job? So basically, this should make sense to you, hopefully. It does certainly make sense to me. If there's an entry-level job and you just started out and you've been with the company 1, 2, maybe 3 years, you're basically entry-level, that person's probably high flight risk. They're probably not going to stay long. They're going to get some experience, put it on the resume and just move on to the next job. Now, if this is a superstar or an overperformer, overachiever, whatever you want to call it, and you want to keep that person, that could be the exception as opposed to the rule. But most of these entry-level jobs, you can see 50%, if you're entry-level category, you're going to leave, high attrition, just get it on the resume for 1 or 2 years, maybe 3 max, and then move on for the next part of your journey, of your work-life journey. So work-life single, work-life married. So 46% of these people are going to leave, 44% of these are going to leave. Number of promotions. So as you get more promotions, you're less likely to leave. If you have fewer promotions, you're more likely to leave. Hopefully that makes sense. Job level senior, 30% outcome on the attrition of the employee, distance from home. This makes sense. If you're far from home and you have a long commute, you're probably going to leave after a while, right? 20% chance of leaving, 21% chance of leaving, and you're going to find another opportunity equal or better that's just closer to your home, right? Just better commute. Work-life balance, if it's not good, 21% of the time people are going to leave for remote work. No, if you can't work remotely, 20% of these people are going to leave, right? Down here, I think we have remote work. Yes, if it's yes, 20% of these people are going to leave. So remote work doesn't really have a huge impact on attrition if the person stays or goes. It is what it is, right? Work-life balance, if it's good, 19% of the people are going to leave. If it's bad, then what is this, like 81% of the people are going to leave, and so on and so forth. So using the SHAP computer, we can determine what is the probability of attrition for each of these categories, right? So I think that's pretty cool. We can go ahead and plot the results here. We have a horizontal bar plot. I'm going to cut that out. I was testing one idea. I didn't really like it, so I'm going to get rid of that. Here's our horizontal bar plot. Let me change this just a bit with and you can change the height of this if you want it bigger. I think 500 is good in this case. That's a little bit overbearing right there. Maybe 600. I'll go 6. This is pixels in terms of height. So 600 pixels high, 1100 wide. And this is just a graphical representation of what we just saw. Job level entry, 50.01, 50.1% of the people are going to leave. Work-life balance, excellent. 10% of the people are going to leave, right? So that matches that. There's a 10% and there's a 51%, right? So hopefully it makes sense. If it's entry level, half the people are going to be gone after a couple of years. If the work-life balance is excellent, 10% of the people are going to be gone. They're going to go no matter what, even though it's work-life balance is excellent. 90% of the people are going to stay, but still 10% are going to head out and go do something else. So let's take another look at another perspective here. This is salary, commute range or commute distance, right? Commute time, remote engagement, manager training, promotion age, overtime, or dependence. Based on all of these different features, we want to try to understand what is the probability of the person leaving, right? We saw some examples over here. This is very useful, I think, right? Attrition probability. This is 20%. This is 60%. And decile 2 and decile 8, right? So anyone that falls into this bucket, 60%, 63% chance person's going to leave. We can try to intervene and get this person to stay most likely. If this is like 90, 95%, that's a hopeless cause. This person's gone. This person's probably going to stay no matter what. Still, I don't think you need to offer a promotion or a spot bonus to this person. They're probably going to stay. 80% chance of leaving, 20%, 80% chance of staying, sorry, misspoke, 80% chance of staying, 20% chance of leaving, so the attrition is 20%. Probably not going to go anywhere, but you might want to have a sit-down conversation with this person, make sure everything's all right, make sure they're happy and well cared for. Okay, so what else? So we have a couple more things we need to look at. We'll wrap it up pretty soon. If the field is salary, There's going to be a compensation review, adjust base pay if necessary, right? Again, if this is a high performer, overachiever, you want to keep them happy, keep them satisfied. Commute, if this is greater than 40, right, 40 minutes or 40 miles from work, then there's a higher chance that the person's going to leave. Remote work, does this come into play? We saw earlier, probably not. It's like 20% chance, right? Remote work, no 20%. Remote work, yes 20%. So in both cases, attrition is about 20%, 80% of the time, whether the work is remote or on site, the person's going to leave. 20% of the time, whether the work is remote or local on site, the person's going to stay, right? So something to keep aware of, or keep an eye out for, and we should be aware of that, but nothing really urgent to do there. Manager, is the manager fair, below or average, right? We have to try to quantify that. Promotion age, is this person in an age bracket that they're eligible for promotion? If you just start out of school, 2020, 20, 21, 22 years old, probably not eligible for promotion, maybe like a small, mediocre promotion. When you get a little bit older, and get into your 30s, 40s, 50s, you're probably more likely to be getting those big promotions. Not in your early 20s, highly unlikely. Overtime, is there overtime or not, right? If you're required to work a lot of overtime, maybe that's a candidate for attrition, might leave. If they hardly ever work overtime, they feel they have a cush job, good money, you're not worked to death, probably going to stay, right? So these are the things we're looking at. Let me go ahead and run this right now. We have all the columns here: employee ID, attrition, probability, risk bucket, job role, monthly income. I don't want to spoon feed this and read everything line for line, but you can read this for yourselves, right? Overtime, recommended action. So this is the key here. Based on all these inputs right here, right, what we saw before, this is what we got in the original data frame. We're going to go ahead and make a recommended action. This field is appended to the last column in the data frame, and this comes from recommended actions and all the fields that we studied above. So recommended actions is the name of this user-defined function. This is the DEF, the function, defined function, right? UDF is user-defined function, or just function, you call it a function, based on the rows. These are all the rows in the whole data frame, and the fields are the column names or the headers, right? Based on all the rows and all the fields. This recommended action comes from here, high risk. This is sorted by training, right? And we are sorting everything in descending order based on attrition probability, okay? So we take all these different features above, right, that we defined in the UDF right over here, recommended actions. So salary, commute, remote, yes or no engagement, manager, happy or sad, are you upset with your manager, delighted with your manager, overtime work, and number of dependents. If you have one dependent or no dependents, you can probably work more overtime, and you're probably more likely to stay with the company. If you have 4 or 5 or 6 kids at home, I know people that have 5 or 6 kids at home, they might leave if work becomes overbearing. They just can't deal with it because you have a household of dependents at home, 5 or 6 kids at home. Hopefully your spouse is taking care of some of that. But you have 5 or 6 kids at home, that still requires more than one spouse's attention. You probably won't be able to do a lot of overtime, long commute, and you're probably going to leave the firm unless the firm can accommodate your needs and your desires, right? So here's the final recommended action. This is why we do everything above, right? So everything from the beginning down to here coalesces, right? It comes to a head right here with recommended actions. Let me run this, Control Enter, and let's see what the model gives us a recommended action. So this is the why everything happens, okay? So the why is the most important thing you can ask. You can say, well, what happened and how did it happen and when and where? These are pretty simple questions to answer. When, where, how, which way, right? But why did something happen? Why did this happen? Why did this other thing happen? Why did some other thing happen? Why did something not happen, right? These why questions are very abstract and very complicated to answer sometimes, but sometimes it's not too hard. If you dig in a little bit, you can try to assess the why. You can try to determine why something happened. If you can answer the question why, then you are golden, right? You can do anything if you can say why something happened. The rest is easy. The why is the hard part. So let's take a look here. So recommended actions: assess role for flexible remote option, boost company reputation, manager 1-to-1. So the meetings are going fine. It sounds like recommendation. Pulse check, boost employee recognition, manager 1-to-1. So maybe more 1-to-1 meetings, maybe to do a monthly, maybe you have to do bi-weekly, maybe it was twice a week and you have to do it once a week. Recognition pulse, clear pathing and promotion. So talk to this person. This is the path. This is your, this is a track for promotion. This is how you're going to get it done, right? So this is this employee ID 17202, probability of attrition 97%, right? But if we undertake these actions over here, we can probably keep this person on the payroll. They're probably going to stick around. We don't have to lose that 97%. So here, attrition probability. I don't know why I keep saying attribution. It's a totally different concept. Attrition probability 97%. So that's high risk. 97% high risk, right? Different employee 63012. This is 17202. 97% likely chance of leaving. This is decile 10. This is decile 10. I'm sure. Yep, same decile. Job role, healthcare, so on and so forth. Number of promotions, got 0 promotions. Really doesn't have a huge motivation to say, but you have to get with this person and discuss the long-term benefits of the person staying here. This is the recommended action. This is the remediation to keep this person here if you want this person staying here. So again, this person got no promotion, 97% likely to attrition, but how can we keep them here and why are we doing this? Assess role for flexibility, remote options. Maybe this person's coming in. Let's see, no is what? Remote work. Okay, no remote work, no remote work. Give this person remote flexibility once or twice a week. Give this person remote flexibility once or twice a week. Don't have to pay more money, no raise, no promotion just yet, but get them on the track to promotion. Say, get this straightened out, get on the path to success, and we'll give you a promotion in 1 to 1.5 years, 2 years, whatever it is. That's what you have to negotiate and determine with the person. But this is the takeaway to keep the person at the company. Set up 1-to-1 recognition, recognizing the person. Manager check-in, boosting job satisfaction, performance recognition, so on and so forth. Remote commuting a couple times a week, keep the person there if they're happy. What's the next one here? 97% chance of staying. Poor says what? Poor says work-life balance. Poor. Okay, we got to work out for this guy. And high is what? This is job satisfaction. High job satisfaction. So I like what they do. Poor. Which one are we on? Oh, this guy right here. Wait. I got lost here. 1, 2. This is 1. This is 2. This is 3. Right. So high is job satisfaction. So very satisfied with their job. Fair is what? Work-life balance. Okay. Remote work. No. So give this person remote work. More one-on-one meetings with the manager. Clear path. Determine how this person is going to get promoted in 1.5 to 2 years. Offer remote hybrid days off. And, who knows, maybe one more vacation day per year or something like that. Maybe a couple more vacation days. This person is likely to take off. 97% chance of attrition. Try to keep the person here. Look, we're looking at the top head, right? And this is in descending order. So we're looking at the people that are most likely to leave, right? Ascending equals false for attrition probability. So we're looking at the most likely to attrition. This is the top 10. Let's look at number 10, 0.96. So we went from 0.97 to even better, 0.96. So 1% less likely to attrition. Decile 10. Remember, we went from 1 to 10, and 10 was the worst, most likely to leave, right? Anything from 1 to 9, I think these people are pretty satisfied with their job and they're not going to leave. Decile 10, they're heading out the door pretty soon unless we intervene. So no says, what are we looking at here? Remote work, no. Give this person remote work options. Work-life balance, what is this? Fair, we should improve that, right? Make that better for the person. Better quality of work life. Medium is what? Job satisfaction. Kind of medium, they're kind of satisfied, kind of not. Performance rating, basically below average. So this is interesting, right? So below average performance, this person is 96% likely to take off, right? Do you really want to keep the person if they're below average? Maybe just let this one go. Might be a drag on the team, might be a drain on, the corporate culture. This one is a little bit different from the others. You might just say, let this person go out the door, let them go. They're really below average performer, and maybe it's just not the right spot, right? I've had jobs where I was a superstar, excelled, blew the roof off the place. I had other jobs I tried, no matter what I did, everything was a failure, right? Like everything, my boss is always out to get me, chasing me around all over the place. I was never going to be successful there, right? Below average performance every single day, never change. Just let it go and just move on and go do something else, right? It's just not very fit, not very culture for whatever reason. So if you want to save the results of the CSV, you can save down everything. This is optional. Leave it up to you. expected net value for 150 interventions. So this is very interesting right here. Now I've quantified the benefit to the firm. You can save 2.634 million if you intervene with these decile 10 people that are highly likely to attrition, right? They're going to walk out the door 90% or more probability of attrition. But if you can get these people, with the exception of this one, below average performance, we don't really want this person, male, female, I don't know what the race, color, the religious orientation is of this person. If they're below average, 96% decile, really like not very happy with where they are. It's just not a right fit, not a good culture. Let the person go. If you can save some of these people, it's going to result in $2.6 million in savings, right? 2.6 million in savings to the bottom line. That's 2.6 million that you don't have to save. I always say that money saved is better than money earned. If you go out and make about 3.5 million extra revenue, you'll have to pay tax on that. The after-tax income is probably going to be around 2.6 million. So it costs you 3.5 million in new business or new revenues, right, to get 2.6. If you can save the 2.6, you don't even have to beat the bushes and get new business. You don't have to go out and get another 3.5 million. Just keep these people happy, keep them employed, keep them on the payroll, and it's going to save the company 2.6 million. If you have decent employees, it's way cheaper to keep these people than to let them go, especially go to a competitor, work for a competitor, take all their skills and knowledge, right, work against you a couple months from now, and you still have to go out and replace the void that was created when that person left, and you have to train a person. It's going to take months to get them up to speed. It's going to cost you a lot more than 2.6 million. I can guarantee that, right? That is a mathematical certainty. So keep the people that have the skills, that have the knowledge, that have the competencies, keep them on the payroll, keep them happy, and it's going to save you $2.6 million. It's quantifiable, and that is non-negotiable, okay? So who does what and why? This is the last thing here, and then we'll wrap it up right at the end. Control Enter to run this. We're looking at different deciles, the attribution, right, the probability of attribution, and then the actual rate of attribution. This is the average probability right here of attribution. These are the 10 deciles. Remember, we had 59,600 records in here, right? If we look at this, we have 59598, so basically 5,600. So we break these down into deciles of 5960 each, 10 deciles. This 10 decile is the one that we want to be most aware of. These are kind of like the losers of the group, or the people that aren't adding a whole lot of value. They don't like what they do, the low performers, just not satisfied with the job. They don't fit into the corporate culture or whatever. So this 10 decile, this is what we want to keep our eye on. Probably urge them out, unless you see a few exceptions. Maybe work with them, get them to stay. Everyone else in decile 1 through 9, we want to keep these people. 1 is the most desirable. These people love their job and they're top performers. 1, 2, 3 goes down a little bit down here. Maybe don't quite love the job as much, but still, meet expectations, still do a decent job. 10, we have to probably get rid of them unless you can find a handful of exceptions. Maybe keep them. Remember, there's 5,960 people here. Are we going to terminate 5,960? Not necessarily, probably not, but we have to focus on these 5,960, almost 6,000 people, and figure out which ones need to go and which ones need to stay. You can see the average probability of attrition is 86%. They're probably going to go no matter what. And the actual rate of attrition is 91%. It's even higher than the average probability, right? So the actual rate of attrition would be lower over here, right? These are the top performers. The average attrition is 10%. The actual attrition is closer to 6%. So that's it, guys. This is my take on predict employee attrition and designing targeted retention actions, how you can keep the best employees happy and satisfied and cared for and well kept. And then the ones that are underperforming and they just don't like the culture, they don't like where they are, they don't want to be there, you don't want them to be there. Encourage them to get out and spread their wings and go somewhere else, and try to not hustle them out, but try to encourage them to get going and go do something else. So that's it, guys. I am going to save this right here, and I'm going to save a copy. I'm going to post this when I post the video. I'm going to put the video up a little bit later today. I'll post all the source code so you have everything you need. You can copy and paste this in your own Jupyter Notebook environment. Run it. You'll get exactly the same results that you see here. So I'm going to wrap it up. Give me some comments. Give me some feedback. Love the feedback. I don't think there's any errors or issues here. This is my take. Some of this is subjective. I try to make it as objective as possible, but some of this, no matter what, is going to be my own interpretation of the topic and my own prior biases and experiences, work experiences, education, my own knowledge. So I'm not saying it's 100% right. This is one way to attack the problem and solve the problem. As always, there's probably many ways to skin the cat. There's probably different perspectives, different ways you can attack this problem and solve the problem. This is one way, okay? So that's it. Hopefully this was educational and inspirational. I'm going to wrap it up. We're going on almost 50 minutes, kind of dragging on. Most of these videos, I try to keep to 25, 30, maybe 35. This one kind of got away from me. Anyways, we're at 50 minutes. I'm going to wrap it up. Thanks for your time. I appreciate it. I will drop the video later today. I'll post all the code, and I'll see you guys soon when I post the next video. Should be sometime in the next couple of days. Take care. See you.